So what is going on, guys? Let's go over this multiple choice, okay? So look, the determinant of A is a product of the diagonal entries in A. What do you think? If you think false, then you're correct, because look, the determinant of A is a product of the diagonal entries only when A is in the triangular or reduced echelon form, okay? Otherwise, this statement will always be false. An elementary row operation on A does not change the determinant. Well, what are the elementary row operations? You have multiplying a row by a scalar, interchanging two rows, and multiplying a row by a scalar and then adding it to another row to form a new row, okay? We know from, what's that theorem? Theorem 3, and I talked about Theorem 3 in the video, that two of the three row operations change the determinant, okay? So this statement is false. We know that the determinant of a product is a product of the determinants. So this is just that statement backwards. The product of determinants is equal to the determinant of the product. So this is a true statement, okay? If lambda plus 5 is a factor of the characteristic polynomial of A, then 5 is an eigenvalue of A. Well, I don't think there was ever a theorem that said that if lambda plus 5 is a factor of the characteristic polynomial, then this value right here, this 5 value, is an eigenvalue of A, okay? So this is flat out wrong. It's false. If A is a 3 by 3 with columns A1, A2, A3, then the determinant of A equals the volume of the parallel pipette determined by A1, A2, A3. Well, this is false too, because look. Sorry. Wait a minute, I went too far. That was section 5.1. I apologize. Right here. When A is a 3 by 3 matrix, absolute value of determinant of A turns out to be the volume of the parallel pipette determined by the columns of A1, A2, A3, okay? So now, let's go back to the multiple choice. They left the absolute value sign out of here, so this is false. Determinant of A transpose equals -1 determinant of A. Once again, this is false. The determinant of the transpose is the same thing as the determinant of A. Or I mean, the determinant of A transpose is the same thing as the determinant of A, okay? The multiplicity of a root R of the characteristic equation of A is called the algebraic multiplicity of R as an eigenvalue of A. Well, you think, geez, this is so much. But actually, they tell you that this is true. This is true statement. Because look. Look what they say right here. The eigenvalue 5 in example 3 is said to have a okay, whatever. That's not the right sentence. In general, the algebraic multiplicity of an eigenvalue lambda, its multiplicity as a root of the characteristic equation, okay? Read this sentence again if you have to. So, what the question says, the multiplicity of a root R of the characteristic equation of A is called the algebraic multiplicity of R as an eigenvalue of A. This is true, and that sentence right there just said so it's true. A row replacement operation on A does not change the eigenvalues. Well, this is false, right? Because look, let me show you where it says that. A row replacement operation on A does not change the determinant, okay? Remember this statement. and then hold on a minute. I think this one's a little tricky. A row replacement operation on an A does not change the eigenvalues. Well, the eigenvalues are related to the determinant, right? And since a row replacement definitely has an effect on the determinant, it's definitely true that we can infer that they also have an effect on eigenvalues. Okay, so though I'm not sure, I would say that this is false. Okay, but I'm pretty much 99% sure on the other 7 multiple choice, but this D I might be a little iffy. Okay, so thank you for watching. I'll see you next time.